theme of the extremes of physics, and we're exploring that in a number of different ways. And in tonight's lecture, we're going to be exploring that in terms of the extremes of light and what we can do with it, especially in other fields of science, as we'll see a bit later on. First of all, before we get going tonight, I'd like to acknowledge the traditional owners of the land on which we're presenting these lectures, these lectures, and just pay our respects to all the Indigenous elders and people who might be here tonight from Indigenous backgrounds, and recognise the ways that Indigenous knowledges are so important to our work in the Academy in the 21st century. So I'm not going to speak for too much longer, because the person you're all here to speak tonight is Dr Eleanor Campbell, who is a beamline scientist at Australian Synchrotron, about half an hour from here. I like to describe her as a crystal wrangler extraordinaire, which I think you'll understand more after her lecture tonight. So without further ado, I'm going to pass over to Eleanor. Could you please give her a round of applause?
Thank you. So I just want to double check my microphone's working. What do you think? Does that sound... One of them's on. This one. I'm just building suspense. Oh, there we go.
I can hear you.
Oh.
And then we went off again.
Got backups.
Sorry, let me give you a backup. If I can untangle it. Why don't you start with this and then I'll put another one on.
Oh, thank you.
You okay to hold that?
Yes, I am. Hello. Oh, I feel very sorry for Susie now having to wrangle cords while I try and introduce the world of light and crystals. I appreciate that sounds like I'm going to be having you joining a cult by the end of the talk. But no, this is some hard physics. I do need to offer a little proviso at the start, which is that I am not a physicist. I am a biochemist by training, so I will be sneaking some biology into this lecture. We're going to get there via the means of physics. Oh, we'll try this one.
Sorry, that's your recording one, and this is your lectern one. So let me swap it.
Okay.
If I can pop. This one's for just for the recording.
Excellent.
Keep going.
I feel like I'm on sort of daytime TV. It's fantastic. So I think the real take home from this lecture that I want you to leave with is that these silos of kind of physics, chemistry, biology, they completely break down at the facility where I work at the Australian Synchrotron. What we do is incredibly multidisciplinary. We're a facility staffed by about 170, 180 people, and these are people from every walk of life, every field. We've got computer scientists, physicists who are specialising in our accelerator. We've got, oh, there we go, tech experts, incredible AV people. How's that sounding? Yeah, all good? Fantastic. We've got, who else have we got? We have thousands of research visits coming through every year, so that means we need an incredible team of administrative staff who can manage all of the scientists coming on site to use our equipment. So it is a place where there are a lot of different disciplines combining, and I'm hoping that that theme comes through during the talk today. So, excluding my lovely colleagues who have come along, who here, this is the only interactive bit, but I am curious, who has heard of the Australian Synchrotron or been through on a tour? Oh, fantastic, all right, I'm preaching to the converted, that's okay. I hope that you get something out of this as well. So we are based in Melbourne's southeast in Clayton, and we are a particle accelerator. So what does that actually mean? Well, we're going to be talking a lot about light today. And I wanted to put up this slide here. This is actually a ruler that's usually on my desk, and I put it in the scanner. So this is a very high-tech piece of equipment that I'm using to demonstrate the electromagnetic spectrum. So a lot of you will be aware of electromagnetism. When we talk about light at the Australian Synchrotron, we're talking about a big range of electromagnetic radiation wavelengths. So if you look right down the end at the far side here, we have our very long wave electromagnetic radiation. And this is the kind of stuff that we get in radio waves. These waves, so from peak to peak of our large wave, they're in the order of meters. By the time we start getting towards the part of the spectrum that you might be familiar with from night vision goggles, things like that, we've got our infrared radiation, and then we start to get into our visual light. So this is the visible light that we as humans have evolved to see. Some animals can see infrared or UV radiation, but we're pretty much stuck in this range. And the wavelength of light that we perceive is kind of on the order of the same size as bacterium. So very, very short wavelengths, very small gap between the peaks of those waves. We start to get into UV radiation, and this is something very close to my heart because I'm ginger and I have to avoid UV radiation at all costs. So my nemesis here in the kind of UV range. And then we start to get into where I think the really interesting stuff happens, and that's in the X-ray range. And so a lot of the work we do at the Australian Synchrotron, not all of it, but a lot of it we do with X-rays. In fact, at the Australian Synchrotron, we produce light 1 million times brighter than the sun, and the light that we make falls into this sort of area of the spectrum. So from the low infrared right up to hard X-rays. This whole gamma ray thing up the top, that scares me, and I will not be addressing that. Yeah, those are sort of the weird things that whiz through space. So here is the Australian Synchrotron, some older drone footage of the place. And as you can see, it's a decent sized facility. The circular building in the center there, that is on par with the size of the oval at the MCG. So if you exclude the stands, we're kind of talking MCG sized. And we've got a number of outbuildings. You can see sort of whizzing around we've got a guest house because researchers are coming from all across Australia and New Zealand. They might spend a week at the facility using the equipment. So they need a place to sleep. We operate 24 hours a day, 6 days a week, and then have a couple of months of shutdown periods for maintenance spread out over the course of the year. So it's all go, go, go pretty much all the time. And we try and keep people relatively well fed and well rested between their experiments. This is a little sneak preview of what's inside the synchrotron. So the view from the mezzanine across the inside of that technical building. And I've chosen this angle because this is where I've been spending most of my time recently. Not in the cage, but sort of next to the cage. The cage is there to keep our robot in. And we can talk about the robot afterwards if people are interested. I'm sort of throwing that out there as bait for questions later. All right, so what do we actually do at the Australian Synchrotron? I've said we make light 1 million times brighter than the sun, but how? We are a particle accelerator. We're actually 3 particle accelerators. And I've got this schematic from the top. We've cut away the ceiling to give you a bit of an insight into how we make the light that we then use for these scientific experiments. So it all starts here at 1 on your map. And this is the electron gun. So we accelerate electrons at the Australian Synchrotron. And these are our negatively charged fundamental particles. You might know them from their work orbiting the nuclei of atoms. But here we separate them out and we whiz them along this branch here, which is the linear accelerator. So this is our first accelerator. And this is a section of the machine that's about 12 meters long. It's made of repeating copper discs that are kept at a really nice sort of 40 degrees Celsius. They're warm to touch. And that's because they have to be so precisely engineered that any thermal expansion in that copper will affect how the accelerator functions. So it's very, very tightly controlled. This is kind of what it looks like. Well, it is what it looks like. It's a picture of it. And you can see those repeating copper discs. Now, by the time our electrons have entered this accelerator and made it to the end of that 12 meters, they are traveling at 99.99998% the speed of light. So it does not take them very long. They are accelerated very, very quickly, and then suddenly they are in possession of a large amount of energy. So what happens next? Next, the electrons enter our booster ring, and this is the part of the machine that is actually the synchrotron. So it's our second accelerator, and this is where our energy is being pumped into those electrons, even more and more and more. We're pumping that in the form of radio frequency, so these large cavities that, the analogy is that if you've got a kid on like one of those spinny merry-go-rounds, the radio frequency waves are just pushing the electrons around a little bit more each lap, around and around and around, increasing the energy of the electrons. But the energy in those electrons can't be speed because they're going at basically the speed of light. So instead of getting faster, they get more energetic, they get more massive, and they become greater in momentum. Here's a little picture of the inside of the booster ring. And I've only just noticed, I think there is an arrow on the floor pointing out which direction the electrons go. I don't know why else that arrow would be there. And they do go clockwise, so that's just a little reminder there for the electrons. And we'll talk a bit about those yellow boxes in a couple of slides' time. So what happens next? Our electrons get kicked out of the synchrotron, out of the booster ring, and into our storage ring. So this is 216 meters in diameter, and it is the final sort of stop for our electrons. They typically will spend 30 to 40 hours orbiting around this particular ring, and we know they're going very fast, but to put sort of some numbers on it, in 1 second the electrons will whiz around that ring the equivalent of traversing Earth 7 times. So every second they're doing 7 laps around the Earth. So that's pretty wild for southeast Melbourne, but there you go. The electrons have to get kicked out of the booster ring into the storage ring, which I just think is a fun analogy. There's a little flicking device that legitimately just flicks out the little bunches of electrons as they whiz past, so it's timed as the electrons whiz through, and deposits them in the storage ring where we can start extracting their energy for our own purposes. I have been lying by drawing a ring and by calling these things the booster ring and the storage ring, because they are not rings. As much as we wish that our science donut was actually donut shaped, it is not. It is more akin to a 50-cent piece. So our synchrotron has 28 corners, and what actually has to happen is those electrons need to be bent around each corner into the next straight section. So they're whizzing along in a straight line, and they have to be deflected so that they can carry on into the next straight section. We do this using bending magnets. So these are large electromagnets. We have a magnetic field that is brought into existence by those electromagnets and then tuned really, really carefully by our accelerator physicists to ensure that the electrons, which are negatively charged, interact with that field such that they bend into the next straight section. So that's what those big yellow boxes were in the previous image. This is one of our bending magnets out on the floor outside of the tunnels so that you can see it in all its glory. I've put my mug on the top corner there just so you get a sense of the scale. I don't know if I was allowed to put my mug on the top of the bending magnet, so we'll keep this between us. But you can see that there's also a sextupole magnet and a quadrupole magnet, and these are positioned throughout the synchrotron as well to focus and steer the beam, ensuring that it stays in the right shape so that we get the optimal results out. So the electrons would be passing through long ways, this magnetic field. When these electrons pass through the magnetic field and their direction changes, their momentum changes, their acceleration changes because they're now moving in a different direction, they lose energy. And a bit like a go-kart screaming around a corner and giving out that loud screeching sound, when our electrons whiz around corners, they release energy in the form of light. Light, I labelled it. So this is one of the sources where we get our ultra-bright light. We're not wasteful though at the Australian Synchrotron. We have all these straight sections as well. And in these straight sections, the electrons are travelling in a straight line, so we're not harvesting any of the energy from them. Until you install something called an undulator. And an undulator is an alternating system of magnetic fields. And when we put those in the path of the electrons have to wiggle through that magnetic field. And the result of that is that it produces a very tight beam of light. I didn't use a coffee cup for this one. This is my colleague Daniel for scale. And this was a new toy that we received at the end of last year. This is our undulator that's going into the new beamline that I'm part of the team that's building, which is super exciting. We can talk more about that. And besides being a lovely colour, it's an incredibly precision engineered piece of equipment that's holding apart really, really powerful magnetic fields so that those electrons undulate through the path of our undulator. One thing I really love about receiving this last year, we were getting all kinds of toys for the new beamline. This one came all the way from Japan. It's something like 8 tons of steel and magnets and cables. And they very helpfully attached the shipping label to it for us, just to assure us they'd only sent one. So we were grateful for that. And as I was saying, because those electrons are taking this undulating path through their magnetic fields, every time they change direction, they're releasing photons. And those photons leave our undulator in a really tight, almost laser-like beam of light. So that's the end of their journey around the storage ring. We're bored of the electrons now. We've got our light. What do we do with it? Well, this is where we get the title beamline scientist. We need to take those beams of light and transport them down those tangential lines. So in 5 here, we take that light, we transport it using a system of optics, so that can be mirrors, we've got lenses on our beamline, slits, things like that, and we bounce those beams of light into our end stations. And this is where the analytical equipment lives. So this is where we have detectors, sample positioners, robots, special environments for charging and discharging batteries, putting things under high pressure, changing the temperatures of things. Anything you want to subject a sample to, there'll be an end station somewhere in the synchrotron that will deliver that sort of result for you. So just to give you a bit of a sense of how these optics are manufactured, this is a very literal mirror selfie. So these were the mirrors that we received earlier this year to help bounce our X-rays from the insertion device, the undulator in the storage ring of the synchrotron, down into our new end station. And so these are basically blocks of coated silicon. And to give you a sense of the effort that goes into making these optics, the largest deviation across the surface of this mirror, in terms of its flatness, is in the order of single silicon atoms. So this is actually, my boss thinks it's one of in the top 100 flattest objects that exist, which is why they're in a case and I'm not touching them. Because yeah, those are very, very precisely engineered mirrors. This is an example of an end station. This is the MX2 end station. And this is the sort of stuff you'll see in end stations around the synchrotron. So things like robots, sample positioning. There's a couple of detectors in here, one out of frame. And yeah, this is where the actual science takes place, making use of that light that we've gone through all the trouble of generating. I'll get in trouble for this one too because it's a photograph of a computer screen, so I do apologise for that. But this I snapped just before I made my way here this afternoon. So I think it says, yeah, 2 o'clock down in the corner there. This is our facility status monitor. So this is giving a live readout of the status of the synchrotron. We've actually got a picture of our electron beam up in the top corner. So that's what the beam looks like on some of the diagnostic equipment. And then we've got this big long list of all the different end stations. This is actually even includes some of the beamlines that haven't yet been built, which is great. Ours is up there, High Performance MX. I like to think of the synchrotron a little bit like a Swiss Army knife. So it's a single tool, it's a single machine, but we've got all these different attachments that are coming off tangentially from that central hub. And each one of those attachments has a different specialization, a different application, specializes in a different type of science. So let's go through some of those applications. We're going to start with spectroscopy. So this is a tool by which you can take light and probe the chemical and electronic properties of different atoms and molecules. So the example picture here, this is the Macleay River. It's in New South Wales, and there's historical mining sites upriver. And the result of that is that there's arsenic and antimony contaminating this particular river. So on the X-ray absorption spectroscopy beamline, scientists are able to take samples of that water, shine our X-ray radiation from the Australian Synchrotron's storage ring, bounce it down the beamline into the end station, and start to analyse the content of that water. And what they're looking at there is things like the oxidation state, what those toxic metals are actually bound to, and if they are in fact in a form that is toxic, or if they're in a slightly more benign form of those metals. So really important work that then goes on to inform things like environmental conservation. Another thing we can do with light is microscopy. So this one you might be a bit more familiar with. This is the making larger of small things. This is a Portuguese millipede. These are little creatures that seem to swarm under the doors of the synchrotron every autumn. We get absolutely inundated with them. This one had the misfortune of dying near the X-ray fluorescence microscopy beamline. And we were talking in the foyer before about how if you have a beamline, you just start putting whatever you find on the beamline. So that's what they did. They put this already deceased millipede in front of the X-ray beam, and you can see that you get this incredibly high resolution image of the creature. And because X-rays penetrate, you're not just seeing a close-up of the outside of the insect, but you're also seeing the inside, inside its little shell. On top of that, XFM, the X-ray fluorescence microscopy beamline, can do even more. It actually does a little bit of spectroscopy as well. They're able to probe the identities of different elements inside their samples as well, because those elements are interacting with the light differently to each other. So in this instance, we're able to see that this millipede has strontium on its shell. It's got little organs or something filled with zinc. These are all artificially coloured, so you can tell them apart. And it's got iron on its tootsies. I don't know what that's for, but clearly it serves some biological function. Another thing we can do with light, and I have assurances from my colleague on the small angle X-ray scattering beamline that I'm allowed to call this blobology, because that's how he refers to it. But this is a technique you can use to probe the shape of globular structures as they move through solutions. So milk is many globular structures suspended in water. It's fats and lipids. And what the scientists have been doing in the last couple of years on the small angle X-ray scattering beamline is looking at how different anti-malarial drugs can be dissolved in milk. And there's a few reasons for this. One is that it's a really cheap way of then delivering that medication. Also, it's a lot less threatening to younger children who might be in countries where they need to take anti-malarial drugs. But drug formulation's a really important science. You can't just dissolve a pill in a different solution and expect it to behave the same inside a biological system. So the scattering experiments can probe how those drug molecules are interacting with the fats and then give an indication of whether they're still in the ideal form to deliver that medication successfully. So, spectroscopy, microscopy, scattering. And now, I will introduce you to my favourite of the things we can do with light, which is diffraction. And this is where it gets physicsy again. So I promised you physics, and we're going to head to a little bit of a demo. So I need to press my document camera 1, and that should bring it up. Yeah, there we go. That looks like a wall. All right, so one of the interesting properties of waves, and you can do this with water, you can do it with sound, and you can do it with light, is that when you have a collimated wave, that is, the wave is pointing in one direction, you've got all of your beams of light or sound or water pointing in one direction, so a laser, for example, and you shine them through a small aperture, I find the result non-intuitive. So I've got this fantastic demo set up by Stephen, thank you so much. And you won't be able to see this, but you'll have to trust me. This little slide contains tiny etchings in an opaque substrate. And these etchings are, the first one is just a straight line, a little slit. And the next one is 2 slits, and the next one's 3 slits, and so on and so forth. So when we shine a laser light through a single slit, the intuitive thing that you sort of expect to see is a single slit of light projected on the wall. And some of you are shaking your heads because you've been to physics lectures and I love it. But can we see that? Yeah, fantastic. So there's our tiny little point of laser light. That's how collimated it is. It's not spreading out particularly much. It's traveling over a decent distance, but still staying very focused and tangled up. And now if we put it through a single slit, we actually see it diverge like this, right? And that's because what's happening is as that wave is meeting that aperture, you're basically creating almost a new light source. It's starting to radiate out in more of a shape like a half moon, sort of moving away from that slit. If you imagine putting a little drop of water on a pond and seeing those ripples spread away from the source of the drop, you're basically seeing that effect from the wave of light passing through that slit. So you get these bright spots and these dark spots corresponding to where the peaks and troughs of that light wave are. Now if we start to move into a slightly more complex system, so we head along to 2 slits, you can see here that we have a more complex pattern of light and dark spots. And this is due to a feature of light waves and water waves and sound waves, where we can get constructive and destructive interference of waves. So where the two peaks of a wave combine with each other, you get an additive effect. You get a brighter spot than the background. Where the peak of one wave meets the trough of a wave, you get cancelling out. And so you get these dark patches. And we can keep going. We can introduce more and more slits, which is going to increase our number of spots and alternating between light and dark. And I just really like how this looks. And I'm very, very grateful for this setup because I was thinking about how I was going to demonstrate this using tools available to me from the local Priceline pharmacy. So I have here a head lice comb, and I've put some electrical tape on it. I'm, as I say, very grateful for Stephen, but it does kind of work. So I'm going to show it off because I went through the trouble of buying a head lice comb. And you can get it at quite a nice angle, and you can see the diffraction, even through the tines of a comb. I've covered up all the tines except for two. So those distinct spots are purely from the interference of the light waves passing through the comb. So you can do this yourself, $12. You can demonstrate the wave nature of light. You can delouse your children. It's a good $12. All right. So go back to the safe world of slides. I don't have head lice. I had to explain to the lady at the counter that no, this is for physics. Are you coming back? Please come back. Oh no, it's a blank slide. I forgot. So here's a bit of an animation of what we were just looking at with the diffraction experiment with the laser. So where we have two waves above lining up in phase with each other, we get that increased amplitude of that lower wave. Where we have the peak of one wave cancelling out with the trough of another, that's where we get our null, our zero. This is a simulation of the top view of what we just saw. So once again, you get a nice sense of this really collimated beam of light or sound meeting those slits, and then the interference pattern as a result. So you get these enhanced peaks at some positions, and you get decreased peaks or the absence of peaks in other positions. It's really nice if you see this on the surface of a pool or something with light shining through. You see the enhancement of the light being refracted through the water, and you get these really lovely diffraction patterns, interference patterns. So what do we actually do with diffraction? We very rarely fire our X-rays directly at small slits in slides. We fire our X-rays through crystals. Not these crystals. Some people at the facility look at minerals. I'm not interested in minerals. They're great, but the crystals that I'm interested in, sorry, geologists in the audience. The crystals I'm interested in look a bit more like this. So these are microscopic crystals, and they are formed from biological molecules. These are formed from proteins. So proteins are very big and wet and floppy, and they do not like existing as rigid crystalline structures. It takes a lot of time and effort to convince a protein to become a crystal. You have to purify it. You have to basically sample tens, hundreds, thousands of different conditions until you find exactly the right soup that's going to encourage your protein molecules to line up in the nice, rigid, repeating pattern that is a crystal. So crystal is anything that contains this nice repeating unit of a shape over and over and over. Now, to give you a sense of the scale of these things, I said they were microscopic. When you're a SAD PhD student working in a protein crystallography lab, you have to pick these things up by hand. So here's a little bit of an example of that. I can tell that this one on the side I took from my Instagram because I'm not left-handed. So there's no way I'm picking up a crystal with my left hand. But to give you a sense of the scale of the tools that we use to manipulate these things, there's a ballpoint pen and one of these sample holding pins. And the tiny little white fibre at the top, that's the loop that we're trying to capture our little protein crystal in. So they're quite small. So a little bit of an animation of zooming in on that sample pin. You can see we try and sort of loop them into a little nylon house so that we can position them in front of our X-ray beam. Why do we go through all the trouble of growing these things and then picking them up with shaky hands and positioning them in front of an X-ray beam? because when we do that, we get a result like this. So this is a protein crystal from my PhD research, actually, and it's being rotated in front of the X-ray beam on the MX beamlines at the Australian Synchrotron. And the result is this sparkling disco ball pattern of diffraction spots. So this is the information that we've gone through all this trouble as biochemists to collect. What's actually happening here? This is a little bit more complex than just those light and dark spots in a line that we saw with the diffraction experiment with the laser and the slit. So what's happening here is we're exploiting some of the properties of crystals. Crystals contain planes of atoms. So you can see here, this is sodium chloride, and this is the crystal structure of sodium chloride off to the side. Repeating patterns of sodium and chloride ions. You can see that there are distinct planes. So we've got 3 planes, top, middle, bottom. We've got planes running from left and right. We've got planes running from front to back. And each of those planes has the capacity to bounce X-rays off it. But there are a lot of different planes. So what happens is an X-ray beam enters into one of the planes of the crystal. It bounces off, and it bounces off at the same angle that it entered. The same way you shine a laser on a mirror, you're going to see the angle of incidence equal the angle of reflection. But we have more than one X-ray beam. Well, we have more than one photon entering the system. We've got a second beam of light. So this second beam has the capacity to interact constructively with the beam above it. But it all depends on how much extra that second beam has to travel. And this is where we get into Bragg's law. I think I found this on Google, but it had an Australian Synchrotron logo on the top of it. I worried that maybe Anton, one of my colleagues, had made it. Nope. Good, because I haven't given you credit. But what it shows you here is the wave at the top entering in phase with the wave below it. When the wave on the bottom has to travel a full additional wavelength, it will meet back up in phase with the wave that it entered with. And so the result is both waves leave in phase. But in order for this to happen, we have to satisfy a couple of conditions. So the distance between these planes has to be a particular distance, and the angle that the X-ray beam is entering the crystal has to be a particular angle. So we can introduce the one equation I've included in the talk. This is Bragg's law. And using some trigonometry, we can see that if that second beam of light wants to be in phase with its friend who entered on that earlier plane, then we have to have it travel that extra distance. So it has to travel a full wavelength or a full number integer times that wavelength in order to leave in phase. The result is that whenever that condition is satisfied, we get one of these bright diffraction spots. There are a lot of planes in a crystal, and so there are a lot of spots. And we rotate the sample through the X-ray beam so that we're sampling lots and lots of different planes at lots of different angles. The result is collecting information that we can then reverse engineer, not just the structure of the planes themselves, but the nature of the molecule that was crystallized. So this is how we get 3D models of proteins. And it's all thanks to these guys. So these are the Braggs. So we've got William Henry Bragg and William Lawrence Bragg. William Lawrence Bragg is the youngest Nobel Prize winner in physics. He was 25. So young people in the audience, that's what you got to beat. And they were from Adelaide. So something good to come out of Adelaide. Sorry, I shouldn't. I'm from Canberra, so I really shouldn't make jokes. I've included some chemistry. This is Kathleen Lonsdale, and she was a chemist, and she was investigating the structure of benzene, which is 6 carbon atoms that sit in a hexagon. There was a lot of debate about whether benzene was a molecule that sat flat in the plane, or if it was puckered, and this caused chemists quite a lot of consternation for a long time. Because it has implications for how you develop synthesis routes, because what parts of the molecule are going to be accessible if it's flat versus if it's puckered. And Kathleen Lonsdale used X-ray crystallography to look at crystals of molecules similar to benzene and determine that benzene is in fact flat. So it has applications in chemistry. This is another person who I was talking about in the foyer before. This is Rosalind Franklin. And Rosalind Franklin, best known for this famous photograph. Now, the embarrassing thing here is that this isn't actually a crystal diffraction pattern. This is a a diffraction pattern from a fibre of DNA. But we claim her anyway because it's using the same technique, so exposing those samples to X-rays and collecting the resulting diffraction data in order to rebuild a 3D model and determine the structure of DNA as this double helix. So really important work in genetics and biology. I really love this photo, or this pair of photos. This is my favourite crystallographer. You have to have a favourite crystallographer. And this is mine, Dorothy Hodgkin. And she was working during the early 20th century. And she won the Nobel Prize for solving the structure of vitamin B12. So a very biologically important molecule. But the work that I really like of hers was on the protein insulin. So insulin's probably a protein that even if you're very against sort of knowing about biology, you'd have heard of insulin before. And insulin has a very important biological role in maintaining blood sugar. It's something that becomes very relevant if you have diabetes and you need to be prescribed insulin to manage your blood sugar. And Dorothy Hodgkin collected crystallographic data on large photographic plates of insulin crystals. She collected those in the 1930s, and in the 1960s she was able to solve the structure. So 30 years it took of taking those individual diffraction spots and reverse engineering where the planes of that crystal were, and the result was she was able to build this model by hand of insulin. I've put a more modern rendering of insulin up next to it. They're not oriented the correct way relative to each other because I couldn't really figure out quite which way up that model was, but that's in the London Museum, and it's sort of a bit of a pilgrimage I had to do to go see this particular structure, because this was one of the first structures of a biologically relevant molecule that was solved using this technique. So incredibly complex, hundreds of atoms, and we can know the atomic position of each one of those atoms. Moving from the world of single proteins existing in cases built from balls and sticks stuck together, I have to show you this animation that was lent to me by the incredible Brady Johnston, who does biological animation rendering. And this is just a little bit of a collection of some of the incredible three-dimensional structures of biological molecules. And these are actual experimental data, so some of it's from X-ray crystallography, some of it's from cryo-electron microscopy, some of it might be from NMR, nuclear magnetic resonance, but this is sort of the field of structural biology. That's a motor. That's from Salmonella, and actually rotates around its axis like a motor. This is sort of a who's who of some horrible diseases you don't want to get. We've had polio, we've had Epstein-Barr, it's not very nice. We've had, that's something that geneticists look at. Don't really know what they get up to. I think we had hepatitis earlier. That one's foot and mouth, that's a fun one. But they are these beautiful structures, and they are molecular machines. They have a physical form, they carry out physical tasks, they mediate basically all of biology. So these things, hopefully not these specific things are in you at the moment. Don't want foot and mouth in the lecture theatre, but structures like these are existing within all of us at the moment, and we can see them. And this is the key, this is the cool thing about crystallography, is if you want to understand a disease or a biological system in order to engineer a drug or investigate some sort of cure or a way of disrupting a particular interaction, it helps if you can see the system, right? The same way you would want blueprints to a bank if you were going to have a heist. You want to know what you're getting into. And it's much, much easier to design drugs for a target that you have a 3D model of. And this becomes incredibly relevant recently. This is one of the COVID proteins. So during the COVID-19 pandemic, when we were all in lockdown, the MX beamlines at the Australian Synchrotron were basically kicked into overdrive because every research group in Victoria shifted gears incredibly quickly to start focusing on addressing the COVID infections. So this here is an example of a human protein. This globular thing is being modelled in its sort of surface representation. And this is the same human protein on the left and right, but it's in complex with two different parts of two different viruses. So on one side, on the far side here, we have SARS-CoV-2, that is COVID-19. And that's its envelope protein. It's a particular protein associated with the virus that is going to glom onto this particular human protein. And then on the other side is the same envelope protein, but from MERS, so a different respiratory disease. And the researchers here, they're from La Trobe, and they were looking at what actually causes long COVID. Because when people get MERS, when people get respiratory diseases like that, they don't see those long-lasting symptoms. And what they found is that the interaction between this particular protein and this human protein is very distinct in both cases. And in the case of COVID, it caused lasting damage to the way that cells could tell basically which way was up. So it affected cell polarity. The cells were no longer able to keep their innards in the correct places. It caused inflammation in the lungs and led to lasting damage. So these researchers were able to probe the exact structural mechanisms behind this particular disease. Another example that we're really fond of on MX is this one here. So this is the structure of a molecule that gets sold as the drug venetoclax. And this is kind of our, I guess it's sort of a bit of a beacon on the MX beamlines, because this is a drug that is incredibly effective in treating chronic lymphocytic leukemia. So something that probably affects a lot of us is different types of cancer. This particular drug was investigated in Victoria by scientists at a number of different institutes across Victoria, and they designed this drug by using structural data that they collected on the MX beamlines. And actually, I was talking to my boss just before this talk, and he said that this quote here about increasing the likelihood of survival over 2 years from 86% to 84%. In later studies where they looked at a 5-year prognosis, without the drug, there was a 2% survival rate, and with was 85%. So that's huge. This drug is licensed in 98 countries now. The first people to receive this treatment were Victorians, because the scientists were here in Victoria testing this drug. So that's something that blows my mind a little bit. We're sitting at the Australian Synchrotron, we're accelerating electrons to the speed of light, we're bending them around corners, producing ultra bright light. We shine through painstakingly grown protein crystals to figure out how to build a drug that can then literally save people's lives. Some people have a mutation in one of their proteins, it's just luck of the draw, and this mutation makes that drug much less effective. So our same researchers are back at it, and this time they're looking at how to design a drug that will have the same impact, but on people who have that particular mutation. And the way they do that is that they compare the structure of the protein from people without the mutation to people with the mutation. They can physically look at the shape and design an interlocking drug that brings about the same effect. So some of the names of the facilities there, you can see it was incredibly across a number of different institutions, and this work's ongoing. And all of that from diffraction. So when you shine a laser through a head lice comb, you're basically kind of channeling the same sort of energy that we've had in crystallography for 100 years to probe into those molecular structures and start prizing apart some of those really big questions in medicine. I want to end it there thanking, I have no idea how long I've gone, it could be 2 hours, it could be 20 minutes, I'm so sorry. But I want to thank the researchers whose work I've presented throughout this. And I want to finish up with this little time-lapse video. So this is the MX3 beamline being built. The demand for crystallography is so great that we have MX1, we have MX2. They're fully subscribed pretty much all the time. So we're a facility that, as I said, runs 24 hours a day, 6 days a week, and we very rarely have any time where this machine, where MX1 and 2 are not filtering through protein crystals rapidly to feed that information back to the researchers who are taking it back to their labs to do work. So we're building MX3, and MX3 is going to be specialised at looking at even smaller crystals. So the PhD students will have to get even steadier hands for picking those up. The beam is going to be brighter and more focused, And the result of that is that people will have to put a little bit less effort into growing these large diffraction quality crystals, and instead they can bring us their less good crystals, and we'll get more information out of them from this instrument. There's a whole host of other amazing features and functions that we're going to bring to MX3, but the end goal of all of it is that we can bring this technology to more and more research groups so that they can speed up the process of doing this medical research, making use of physics, so bringing it back to that multidisciplinary thing. I hope I've imparted to you how we kind of don't sit in one camp. We tend to move across physics, chemistry, biology pretty freely. So yeah, thanks very much for listening.
Amazing, Zoe, I'm coming downstairs. Thank you so much, Eleanor, for such a wonderful lecture, and such a great introduction to crystallography.
Go back to my
And
crystal.
I'm very impressed that your demo worked beautifully the first time. Even your haphazard
I know!
made
I was so
out of light
excited.
stream. I'm just clearly an experimentalist. So we've got a bit of time now for questions. And I've got a second microphone that I might ask Harry if he's willing to be on that side of the audience for questions. Thank you so much. That's it. Yes, you're first, so please go ahead.
Thanks very much. Knowing the amino acid sequence of the protein, artificial intelligence is now being used to determine the structure of that protein. How accurately is that in comparison to measuring the 3D structure using the crystallography?
Yeah, that's a fantastic question, and it's one that was keeping us awake at night building a new crystallography beamline. Because yes, AlphaFold being developed by Google's DeepMind is very, very good at predicting the structure of a protein based on its amino acid sequence. This has put a couple of different fields of science on the back burner. So I skipped over some of the complexities of determining the structure of a protein from its diffraction data. We actually only really get 50% of the information we need from those diffraction spots. What we also need is information about what phase that wave was in when it hit the detector. And we can't get that from the detector itself. We have to get that from other sources. So we can determine that experimentally by soaking heavy atoms into our proteins, which scatter light in a predictable way, and we can reverse engineer what phase those waves must have been in when they hit the detector. Or we can bootstrap the data using existing models. So if you've got, say, pig insulin, you can use your model of pig insulin to solve the structure of human insulin, because they're similar enough in structure that you can start matching the reflections that you've collected on your detector back to that previously existing model. So AlphaFold is fantastic at giving you a best guess at your protein structure that then allows you to solve the diffraction data that you've collected. This means that people who do experimental phasing are finding other jobs because it is incredibly effective. I like to think that as experimentalists, even if we have a really, really good tool for accurately predicting the structure of proteins, we will still want to verify them experimentally. And AlphaFold is going to be a tool that helps us do that faster and lead to hopefully a quicker turnaround on these drug discovery projects, but I still want to have the experimental data in addition. But yeah, really good question.
Can AI help you pick up crystals?
Oh God, I wish. Oh, we're not there yet.
There's another one up here. Thanks, Harry, for taking the microphone. That seems to me always, when I chat to you, the hardest part of the job.
You have to figure out, you know, you got to eat something beforehand.
Yeah, get your
Hand steady, yeah.
With the instrument before
Yeah.
you can get.
Yeah, look, your lecture had everything in it. 6 poles, MX performance. I was at a motorbike track yesterday and glasses of milk. What I want to relate it to is the silicon mirrors that you talked about, that they are so flat. Do they react in the same way as engineers' metals? When you combine them together, they have a force that's really not known why. They stick together and you can't pull them apart.
Oh, like cold welding kind of stuff.
Yeah, so that's my first question.
Yeah.
And my second question is, the private companies that came up with the vaccines for COVID,
Yeah.
they don't have their own synchrotron, so they would have used a lot of public money for their research. So how is that negotiated on pros and cons of dollars and cents?
Oof, Well, I'll answer your first question, because vacuums. So yeah, I can't say for sure, but I suspect if you've got these two really flat, identical silicon surfaces and you put them in the vacuum of space, they won't be able to tell which one is which. They'll become one being, because there's no distinction between the atoms. So yeah, we do have all of our optics under vacuum because we don't want our X-rays colliding with any particles, but not under high enough vacuum that I think we'd see cold welding. In terms of the money stuff, above my pay grade, I'm so sorry. Yeah, it's very complex, and it's one of these things that we have to continue to talk about, you know, where we get our funding from, and then open access is a huge thing that we push for. We want all of the research done to be available. One of the things we're really pushing for on MX3 is all of our software is going to be open source. So we're writing all of our own pipelines to process the data, and we're making all of that open source so that at least a little bit that we can contribute to the public good, we can kind of push out there. But yeah, big pharma, whew. Yeah.
I do remember cancer. There's 1 year old cost.
Oh, don't worry.
Sorry, for the camera, we'll put it on. Thanks.
Sorry,
Still on the subject of those mirrors.
how do they get them so flat?
Or how do they, so
You said one of the top 10 flattest in the world or something.
yes,
So you clicked on
top 100. We're not claiming top 10.
how do they do it?
So how do they do it? They do it with scanning electron microscopes. So they're actually able to visualize individual atoms by using electrons as their light source rather than photons. And then they actually will use very precise lasers to plick off individual silicon atoms. I heard that one of the companies we were looking at, they will submerge their mirror surfaces, their substrates that they're going to put the mirror on, under a solution of water and some very, very gentle abrasives, and then they'll just run water across it for months and months and months and months. And apparently it was inspired by Japanese monks watching water move over stones, but I think that was just marketing because it was a Japanese company. So, but yeah, so they'll seek and destroy individual silicon atoms.
The one of it.
What does the robot at the start of the slide?
Thank you. Yes, so we have robots on all of our MX beamlines. One thing I didn't mention is how high throughput MX is. So I mentioned that some researchers will come and spend a week at the synchrotron doing experiments. We have researchers who will spend 20 minutes at the synchrotron doing an experiment. We can collect a data set from a protein crystal in about 20 seconds. So people will bring hundreds of samples. And because of the nature of the beamlines, they're all shielded behind big lead doors so that we don't get any radiation leaking out. It'd be really tedious for someone to have to mount a sample, head on out, do the safe search and secure process to close it up, collect for 20 seconds and go back in and repeat the process. So what people actually do is they pick up their protein crystals, they snap freeze them in liquid nitrogen, and then they ship them to us under liquid nitrogen. We load them into the robot, and the robot mounts them for the users, and they can control the robot remotely so that they can just click one sample after another. Our new system, it'll be about 7 or 8 seconds between samples, so we're going to be churning through a lot of crystals. So yeah, it's for throughput.
Does it have a name?
No, we don't name our robots.
Well, in case you get too attached.
Yeah, I feel I've crashed the robot a couple of times, but we have to in order to learn what not to do with the robot. So I think I'd feel worse if it was named. But I did stick googly eyes on it. Actually, I stuck googly eyes on it with blue tack, and my boss pulled me aside and he said, "Did you stick these eyes on with blue tack?" I was like, "Yeah, I'm sorry, I'll take them off." And he said, "No. If you're going to put eyes on it, like araldite them on so that they don't fly off mid-experiment." I was like, "Oh, okay." So they're properly stuck on now.
What's the process by which you extract the filter or whatever the particular frequency you need?
Yeah, that's a fantastic question. So yes, the light that comes out of our storage ring is an array of different wavelengths of light, from infrared right up to those harder X-rays. So the process for selecting those ranges that you want, we use, on the MX beamlines, we use something called a double crystal monochromator. So a mono 1 chromator color. And basically what we do is we have 2 silicon crystals held at sort of apart from each other, parallel. And by moving them relative to each other and changing the gap between them, we can bounce just the wavelength we want off the first crystal onto the second and then back down the rest of the optics. So using that method, you can actually scan through and select the energy that you want and reject the rest of the X-rays or whatever wavelength of light you're trying to reject. And some beamlines have a few different systems where they'll have filters as well, but some combination of using a monochromator to physically move into the path of the beam of light and extract the beam you're interested in.
How do you make sure that you don't waste the light?
Oh, yeah, good question. One of the beamlines, actually, their screensaver says never waste a photon. And yeah, so that's kind of that's a very deep question. I mean, what is a waste of light? Because we're operating constantly, so 24 hours a day, and we do have a really packed user program. Most of the time, people are on the MX beamlines collecting. With the other beamlines, they might not have users on, but we're constantly topping up energy into the synchrotron so that even if we're losing light energy, it's being topped back up with that radio wave energy. And the result is that we're always keeping a fixed energy available for us to start siphoning off when we need it. But yeah, really good question.
How many other synchrotrons are there, and how often do you talk to each other?
So we're the only one in Australia. I think we're one of 2 and 1 being constructed in the Southern Hemisphere. So I think there'll be 3 of us in the Southern Hemisphere. And I think there's something along the lines of 50 or 60 worldwide. There are some quite cute little wee ones, and then there's huge ones like the Big Particle Accelerator in Grenoble, which is a couple of kilometres around. I think they have little bikes that they use to get between their beamlines. We've been talking a lot with collaborators at other synchrotrons recently for the build on MX3 because we're going to be borrowing a lot of the tools that they've already established at their synchrotrons. So I think you'll find that a lot of the beamline staff, even informally, talk with their sort of equivalents at other facilities, share code and different pipelines and software processing tools, and yeah, kind of keep in touch to make sure that we're not trying to reinvent the wheel if they've already come up with a good way of mounting microcrystals in front of the X-ray beam. Yeah.
Hi, I just wondered how you utilise the space in the centre of the synchrotron.
Oh, poorly. We have floated the idea of a ball pit. It has been rejected by safety. So the space in the very centre is called the bull ring. So we have the bull ring in the very middle, and it's usually full of equipment that's being commissioned. So I think at the moment there's a huge vacuum vessel in the bull ring, and it's sort of a place where our technicians can leave large instruments and equipment that they want to then eventually put into the synchrotron itself. They have to actually lift these 9 or 10 ton cement doors off the synchrotron itself so that they can move equipment in. So yeah, it's sort of a staging area.
Would it be dangerous for someone to be right inside it when it was actually operating?
No. We have been monitoring the radiation that is produced by the machine for, I think, since the synchrotron opened in 2007, and have never seen anything above background. So, except in some specific spots during some specific operations. So if you're switching the synchrotron off and scraping the electron beam to stop it, you can produce little flares of radiation, but there's an exclusion zone around that. We have very, very thick concrete walls, very, very effective shielding, and people can choose to wear their radiation monitor badges, but no one's ever reported higher than background. So yeah, it's pretty relaxed.
I think we've got time for one more. Harry, if you'd like to choose the last one.
Thank you for the wonderful presentation. What's the energy usage by the synchrotron per day, or whatever the measure is?
Yeah, good question. I can't give you a number, but I can give you an equivalent. We use about the same amount of electricity as a large shopping mall. So Chadstone, down the road from the synchrotron, I think we're on par with that for consumption of electricity. So, you know, you can shop or you can shoot X-rays at crystals. Yeah.
I know which one I do.
Sometimes a bit of both.
Bit of both.
Yeah.
Harry, would you be able to grab the gift that's sitting behind you over there? Thank you so much. I think you'll spot it. Thank you. I did not brief Harry for this job. Yes, thank you so much. I'll come and grab it. And in the meantime, we can give Eleanor another massive round of applause.
Thank you. Oh, thank you so much. Thank you. There we go.
There we go. And just, I know a lot of you attended all four of our July lectures in physics, which is amazing. So if you're coming up next week, special treat is Professor Olivia Kilborn, who's actually the chief scientist of Swindon University. He's going to be talking to us about dark galaxies surveying the unseen universe. And if you're a keen listener of Triple R on Time Go-Go, she'll be on there on Sunday at about 11 a.m. discussing that as well, if you'd like a little preview of that. And just finally, if you're super keen on physics public talks, you notice I'm not in the lineup this year, personally. That's because I was already committed to give another public talk at the Convention Exhibition Centre, which is next Thursday evening, if I got the day right, if I remember. And that's also a free public talk